Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the lecture 12 of time domain analysis, right? So previously we did the theory part, right, for steady state error for non-unity feedback. Okay, so in this question, right, we have to find the steady state error of the following system for r of t equals to 3u of t, right? For r of t equals to 3u of t. So I have been given this system, okay, unity feedback, and I have to find the steady state error. But is anything else given? Yes, we have been given the impulse response as a function like this one, which is a decaying exponential, and its initial value is 0.4 and it is decaying at and the value at t equals to 0.2 seconds is 0.147. So what you can observe is, like, if you write this in a calculator, you can observe that this is like 36.7% of this value, right? 36.7% of this value. So like for a decaying exponential, the time constant is defined like it's just for a decaying exponential, right? The time constant tau is defined like when it reaches 36.7% of its initial value, right? So yeah, this is basically 36.7 so of its initial value. So this is the time constant of this exponential, right? That we know. But what can I say if I know the impulse response of a system? What can I say? Basically, if I do the Laplace transform, what will be that transform equals to? That will be the transfer function of this whole system, right? So if I apply impulse and the impulse response that I get, now if I apply a Laplace transform of that one, that will be my basically transfer function of the whole system. That is already taught, right? So again, I will just revisit once, just write in rough. So my transfer function is y of s upon r of s equals to t of s. Now r of s for impulse is 1, right? Laplace transform of impulse is 1, so it will get multiplied over here or like divided, whatever you want to say. So my transfer function will be simply equals to output only. Okay, so yeah, that's how we can say. So what is my error for this is simply a unity feedback. What is my error signal? Steady state error. So my steady state error ESS equals to limit s tending to 0 s, just use a simple formula, right? S r of s into 1 minus t of s, right? Okay, because what things I need to know? I need to know the input, which I know, okay, and I need to know the transfer function, which obviously is given here, right? So like I just take the Laplace transform of this one, I will get a transfer function. So basically, right, what I will do, what is this A? So from question basically my A will be equals to 0.4, right? That is the initial value. Okay, A is equals to 0.4. Now what is my tau? Tau is basically this one, right? 0.2. okay, so my tau will be equals to 0.2 seconds. Okay, so my equation will look something like this. It will be e raised to power minus 0.4 e raised to power minus t upon tau. Okay, so what is the Laplace transform of this one? So this will be 0.4 only, but here, right, it was s plus a. Okay, s plus a, 0.4 by s plus a. So what is my A? A is 1 upon tau. Okay, so like A is 1 upon tau. So how will I write? I will write like this one, s plus a, which is 1 upon tau. Like e raised to power minus at has Laplace transform of s plus a, so it will be 1 upon tau only. Okay, so 1 upon tau is 0.2, right? 0.2. So this is how I can write. So now, right, now what you do, put this value of transfer function up here, okay, and then you find the steady state error, right? Then you find the steady state error. So what do we get? Basically my r of s is 3 times ut, right? So this is basically my I will write this is basically my transfer function, right? 0.4. okay, I need to multiply 0.2 also. So if I multiply 0.2 on both denominator and above, so it will be simply okay, this will be simply 5, right? Sorry, this will simply be 0.4 by s plus 5. Okay, so yeah, now let us apply in our formula, right? So my r of s is 3 by s. R of s is 3 by s. Okay, so what is my E steady state? E steady state equals to s plus 5. Okay, so now simply put s equals to 0. What do I get? So this is 3 outside and this is 1 minus 0.4 by 5, right? So this is equals to 3 into 1 minus 0.08. okay, and this is 3 into 0.92. okay, so this is 2.76. so this is basically my steady state error. Okay, so this will be my answer, right? So like I hope you understand, I would like you got the point, understood that how I find the steady state error. So I have been given the transformation, so I will not write this in terms of that formula, that open loop, right? 1 upon gs. So this can also further be reduced if I have a unity feedback as limit s tends to 0 s r of s by 1 plus s. okay, so this I can further reduce. okay, so yeah, this is what my steady state error is. So but I don't want to do this because I have no information about g of s, but I have information about the impulse response, that is the t of s, right? T of s I know, so I want to use this formula only. okay, so just be careful which formula you want to use and you don't want to use, right? So yeah, that one was this one. So now let's solve another question. So in this question, this is a gate question, previous one also was gate question. So in this question, the steady state error of a unity feedback linear system for a unit step input is 0.1. okay, the steady state error of a unity feedback linear system for a unit step input is 0.1. it is given. okay, so for a unit step input I am getting finite error, so obviously this will be type 0 system. okay, that we know. Now the steady state, as this is a unity feedback system, right? The steady state error of the same system for a pulse input having a magnitude of 10, the magnitude is 10 here, and duration of 1 second. okay, then what will be the steady state error, okay, of the same system? So what we have to keep in mind here is like in how can you do this intuitively? How can you do this intuitively? So intuitively, right, what you can think, if I am talking about the steady state error, okay, I am at t equals to infinity, right? T equals to infinity. So this is just for some transient state. This input is just present for some transient state. So this signal is similar to like impulse, obviously not exactly equal to impulse, but similar to, because I'm just applying it for some time, then taking it away. okay, taking it away. So what happens to impulse? If I apply impulse, then I take it away, then the input is 0. If my input is 0, obviously my system output will also be 0, right? Nothing will be present. okay, so from where the energy will come? Obviously my output will also be 0. So I'm taking away the input also, okay, and the output is also 0. So what will my error? Error will be 0 only. okay, error will be 0 only. So you can think it like that one, you can think it like that one, but obviously through equation will prove this one. okay, so method 1, I will do the method 1 with the help of simple formula. Method 1 is formula, right? So if method 1 is formula, so basically, right, my what is my formula? It is again the same for a unity feedback. It is the same formula, that ESS equals to limit s tending to 0 s r of s 1 minus t of s, right? Or here, like, what is the thing here? We haven't given the unit step input. okay, so like if you remember well and good, I mean the error for unit step input is this one. So if you remember well and good, what was the formula? Like we can do this in terms of acceleration error coefficient also, right? So this will be equals to simply 1 upon 1 plus k for a unit step input. But if the step wasn't unit, if it was some other value, so I will have to multiply some other value here, right? So this is this was unit step only, that is fine. Okay, so I can find my Ka from here. And what is K? K is basically g of 0, right? K is basically g of 0. Or if you don't want to do like this, if you directly want to do from scratch itself, so what you can do is simply write in this equation, right, that this is equals to simply my r of s is 1 by s, so this becomes 1 minus g upon 1 plus gs equals to, what is this? This is 0.1. Okay, so this is equals to simply 1 plus g of s. Okay, and like I put s equals to 0, so okay, I will put s equal, okay, I will put s equals to 0 at latest stage, so let me write this s only. This is waste of time because you already know all this, but still for few people I have to derive this one. So this is simply, if I take the g of 0, so this will be g of 0 is equals to 0.1, right? So what will be my g of 0? So if I find my g of 0, it will be simply equals to, here it is 10, it is equals to 1 plus g of 0, which is g of 0 equals to 9 itself. Okay, so my g of 0 is 9. So now what will be my steady state error for when the input is pulse? So this time my input is for pulse input. Can you write the Laplace transform? Can you write the Laplace transform? So how to write the Laplace transform for a pulse input? Okay, that also we'll see. This is my r of t input, and this is the pulse, right, pulse, and my pulse width is 1 second. Okay, and my height is 10. Okay, so can we write the time domain expression for this one? What will be my time domain expression? So my time domain expression basically will be this 10 into u of t. So initially I'm getting a step, right? Initially I'm getting a step. Okay, this is like a combination of two steps. One is the positive step, and then again I'm adding a negative step with it to make it 0. Okay, so what I can write this as like this one, right? So this will be a combination of two steps. Okay, let me tell you this one. So this is t, and this is simply a step of magnitude 10. Okay, which is starting from t equals to 0. So this is, let's say, r1 of t. Okay, and another step of, obviously it has also magnitude 10, but the direction is opposite, because I have to subtract this one. I have to make my amplitude 0 at this point. So at t equals to 1, I will get a negative step, right? Okay, and this one will be my minus 10. Okay, this is 1, and this is r of t, basically r of t. Okay, so yeah, this one is this one. So how can I write this combination? So the first one I have already wrote it. What is the second one? Second one is minus 10 into u of sorry, this is 10 into u of t minus 1. So this is equals to my r of t, basically this is equals to my r of t. Okay, so yeah, this is my r of t. Now right now can I take the Laplace inverse of this Laplace transform of this one? So what will be the Laplace transform of this one? So if I take the Laplace transform, okay, this is r of s. Simple unit step, I know this will be 10 by s. Now what will be this one? Simply it is shifted by 1 second. If it is shifted in time domain, then what will happen in Laplace domain? Simply, right, this will become e raised to power minus s, right? E raised to power minus s. So this will be e raised to power minus s divided by s. Okay, that is what basically this one means, right? So now, right, so let's put this in equation. Basically what do we get? So my steady state error will be equals to simply limit s tending to 0. This r of s is like s times this 10 by s minus 10 into e raised to power minus s by s Okay, then what is this? This is 1 minus t of s. 1 minus t. What is t of s? T of s is simply this one, right? What was this? This 1 upon g of 0. Okay, 1 upon what I can write here is 1 upon 1 plus g of 0. Okay, but what you will observe is this won't even matter. Okay, g of 0. Okay, now what you will observe is if you multiply with s, this s gets cancelled, and if I put, okay, I will still not write it. This is limit s equals to 0. This will become 10 minus 10 e raised to power minus s. Okay, and here I have, okay, this is not, sorry, this is not g0, this is, that's it, only simple g of s only. Okay, now this is 1 minus 1 plus g of s. Now if I put s equals to 0 over here, what do I get? This becomes 10, and 10 minus 10 is 0, so 0 multiplied by this becomes 0 only. Okay, so like from here we can observe that my error, steady state error is 0 only. Okay, so like this one also we can observe. Okay, or what is the method 2? Method 2 is again time domain, right? Time domain expression. Method 2 is time domain expression. So if my method 2 is time domain, then what will happen? Basically, right? Basically, where was I? So my e of t will be equals to r of t minus c of t. R of t minus c of t. Okay, my e of t is equals to r of t minus c of t. So this is what my e of t is equals to. So what is my r of t? R of t is simply like, what is the steady state? Steady state, it will be e of infinity equals to r of infinity minus c of infinity. Okay, is it c or y? However written. Okay, nothing is written, so I will just write c of infinity. Yeah, it is c of infinity. So r of infinity is 0 only. Okay, so like basically it's a pulse input, right? Infinity it is going to 0 only, right? So this will be 0. Now what is my c of infinity? So for c of infinity, I will again apply the final value theorem. Okay, and what is the information we know? Like g of 0 we know, right? G of 0 equals to 9, we know this already. Okay, so now how to apply the final value theorem? So c of, okay, this is simply using the Laplace only. So c of infinity will be equals to limit as s tending to 0 s times c of s, which is equals to limit as s tending to 0 s times, what is c of s? Equals to r of s into t of s, which is equals to r of s into g upon 1 plus g of s, right? G upon 1 plus g of s. So this is my simple t of s, right? Now what is my r of s? R of s is this right, this one is my r of s. Okay, again this one will go to 0 only. Okay, so my c of infinity will be 0 only. So I'll just copy this one because this will just waste time. One plus g of s, right? So yeah, this is basically what I get. So if now I put limit s tending to 0, this will be 0 only, right? This will be 0 only. Okay, because it doesn't matter. Okay, g of 0 is some finite value. Okay, this doesn't have any pole at s equal to 0 or 0 at s equal to 0. So this is some finite value, and this is going to 0. So this will be 0. So my c of infinity will be 0. Okay, c of infinity will be 0. So my c of infinity is 0. Then obviously my e of infinity will also be 0, because it was simply equals to minus c of infinity. Okay, but intuitively also we can understand, right? Impulse I'm applying as some, like it's something like impulse I'm applying and suddenly taking out the input. So obviously my output will also be 0. So hence my error signal will be 0 only. Okay. So yeah, this was this question basically. So now let's solve for the next question. So what is the next question? So next question, right? We have a open loop transfer function and we have a some type. We don't know the type, like what type is it type 2, type 1, we don't know. Okay. So we have this open loop transfer function, then we have this basically block diagram. Okay. So we have been given that the steady state error is 0 for unit step and is 6 for unit ramp. Then find the value of the parameter p. Okay. So we have to basically find the type of the system. So what the question is telling us is the steady state value is 0 for unit step. Okay, that we know, one condition. And it is 6 for unit ramp. So it is finite for a unit ramp input and it is 0 for a unit step input, right? 0 for a unit step input. So to find the value of parameter p. So how to find the value of parameter p? So like we can understand. So when the type is 1, then for type 1 system my ramp for ramp input I get a finite error, right? That's why here I can directly answer this one, that it will be 1. Okay, but still if you want to prove it, like if you want to do calculations, we can do. So method 1 is basically we already have the information. Okay, basically there is one more shortcut that I will tell in summary. So summary we will do. Okay, there also I will tell, write down the points, key points which we need to remember, right? So method 1 is, we know that for ramp input I'm getting finite error. So if I for ramp input I'm getting finite error, then what will be basically by type for ramp input, if I get finite error, then the type will be 1, type 1 system. So type 1. So if it is type 1, so my p will be equals to 1. P will be equals to 1. Okay, so this is basically my type 1. Now what is the method 2? Simply solve it, right? So what is my steady state error? Okay, so it is telling me that I'm getting 0 steady state error for this one. So what I do, I will directly find the steady state error for unit ramp. Okay, so for unit ramp my R of s will be equals to 1 by s square only. So what will my steady state? My steady state will be limit s tending to 0, which is s 1 by s one minus simply transfer function, right? So yeah, g of s have been given, so I can write that formula now. Okay, I will switch between formulas. Okay, so these are simple to remember, that this one was R of s into 1 plus R of s is R of s divided by 1 plus g of s. So I will write it down. So E of s s s R of s divided by 1 plus g of s, right? So what is this equals to? This is equals to s R of s 1 plus g of s. So this is equal simply s into this. This I have already wrote down here. Okay, I will just write 1 plus g of s. Okay, so this will be 1 by 1 plus g of, what is g of s? G of s is this mass, right? So it is s plus 1 divided by s to the power p into s plus 2 into s plus 3. Okay, so g of s is this mass. So now, right, if I further simplify this one, what do I get? So ESS, so ESS is some finite value. So this is equals to 1 by s basically into s to the power p s plus 2 s plus 3 divided by s p into s plus 2 into s plus 3. Okay, so now, right, this is s plus 1 and this is this one. Okay, so now I have one s term over here. Also I forgot to put this limit s tending to 0, limit s tending to 0. So what is the main thing? I have one s term over here. Now I need to cancel this one. Okay, now what will help me cancel this s term? Obviously some 0, obviously some s term here, right, at the numerator. So how many s terms I need? I want a finite steady-state error which is equal to 6. So definitely I don't want the s to be more than the power of this one, because if there is, let's say, s square, if there is s square, then this one s will get cancelled, but one s will still be remained. So if one s is still remained, so this will be, if I put s equal to 0, now this whole numerator will go to 0 and my error will go to 0, which obviously isn't, right? It is 6. So I need the power of s, this is same as this one. So this one power is 1, so hence this power is 1. So p equals to 1. Okay, p equals to 1. So yeah, from here also I can understand the p equals to 1. So yeah, you can solve like this one also. P will be equals to 1, or you can just solve it in seconds if you know the information, right? That my order of the input and the type should be same for getting some finite error. This I will write it down in summary point, there you will understand. Okay, now we have another question. So in this question, right, okay, if these types of question come, then you don't think about anything, you just find the error at this point using Laplace. Okay, because this time, right, it isn't asking like we have to find the steady state error due to unit step disturbance. Okay, that is important. Unit step disturbance input d of s in the below figure, not due to this obviously it is reference. So my output will be the combination of this input and the disturbance. So if it is asking us to find the error due to this disturbance, what you will do, you will simply, like, we know superposition, right? This r of s will be 0. Okay, r of s will be 0. I will simply find the expression for e of s and then use the final value theorem and then get my desired answer, right? So yeah, that's how you do. Don't get confused by anything. Only if my input is there for a single system, CISO system, the error you will compute like that method that I told you. But for this type of system, you don't need to compute anything. Okay, I mean, you don't think anything, just find this error signal at this actuator point and then find the steady state value using final value theorem. So yeah, we will solve this one. So let me take the block diagram, and this r of s will be 0 this time. R of s will be 0, right? If r of s is 0, then what will happen? Basically now what will my e of s will be equals to? My e of s will equals to minus c of s, right? Because this is basically 0 minus, this was basically r of s minus c of s. So this is 0, r of s is 0, so this is basically minus c of s, right? Minus c of s. Now but I need to find error in terms of disturbance, so I will find c of s in terms of disturbance. So I will go on in this loop. Okay, again that second chapter is coming into action, block diagram, right? So here I have c of s. Okay, at this point I have c of s, which is getting multiplied by 40. So at this point what I will have this is c of s, right? This minus c of s, sorry. So this will be minus 40 into c of s, and what will be this, right? This will be basically here I am subtracting my d of s and this one. Okay, with this I am subtracting my d of s, so this will be minus 40 into c of s minus d of s, right? So yeah, now what I do, I simply multiply this one with this one, so I get c of s. So now I will write the equations. I multiply minus 40 into c of s minus d of s times this whole transfer function 1 by s into 1 plus 5s equals to c of s. So this is equals to minus 40 . into C of S. So now I will write my C of S in terms of D of S. So I will take my C of S on the left hand side and D of S on that side. So C of S I will take common. So this, right, this becomes okay, I will take the minus common here. So this becomes minus of S, oh, this is 5s square plus S, okay, then this is plus 40, and this is equals to my D of S. Here I have D of S, right? So I will write C of S equals to minus D of S by 5s square plus S plus 40. Okay, so this is my C of S equals to, now I'll put this C of S in equation 1, this error signal, this is my equation 1. So putting C of S in equation 1, what do I get? So I get this E of S equals to minus D of S divided by, also, like, this is my E of S. Now I have to find the steady state error also. So this will be 5s square plus S plus 40. So I have to put limit. Okay, what is my D of S equals to? D of S was for a unit step, right? As the question told us, for a unit step disturbance input. So D of S I can put here. Now I will find the steady state error. So this will be limit S tends to 0, S times this E of S, okay, which is equals to limit S tending to 0, S times this 1 by S, because this is a unit step disturbance, divided by, simply all these things will vanish. This is 5s square plus S plus 40. Okay, so this is equals to limit 0. So I will put simply S equals to 0 here. This S is getting cancelled, right? So this will be 0 and plus 40. So I am getting 1 by 40. Now what is equals to 1 by 40? So 1 by 40 is simply equals to 0.025, I think. So 0.025. Okay, this is my steady state error. So this is my answer. Okay, so you don't need to do anything fancy. Okay, whenever you say disturbance, right, just calculate the error at this node, okay, using the Laplace transform, and then use the final value theorem. Don't need to do anything fancy. Okay, so just keep in mind. So yeah, I think that's it for this lecture. Now the next lecture I will solve few more questions from the overall all of the topics that we learned till now. Okay, yeah, thank you for watching.